yesterday. Okay, are we all good? Just let me check that this is recording. It is recording. Is it recording? Yes, it is. Okay, great. So last time I forgot a condition. So what it says is let n be bigger or equal to 2, then z mod n z is an integral domain if and only if n is prime. Okay, so please put this condition before. It's very important. Thanks to the one who asked a question about it, and I realized that. Yes, sir.
For the exercise session yesterday, after you cut off, I don't know, something happened with it.
Yeah, my computer crashed.
Oh,
yeah,
so I'm assuming that was the end of it.
Yeah, yeah, exactly. Well, I mean, we did. Yeah, but
Yeah.
that's okay. Yeah. Okay, so if and only if n is prime. Okay, we proved this yesterday. Or not yesterday, on Monday. Okay, so now we'll continue. Please fix that in your notes. We'll continue. Last time, what did we prove? We proved that the field is an integral domain. Remember, this is the last thing what we did. This is the last thing we did. That a field is an integral domain, right? Okay, now let's prove a theorem. An important one. Or a proposition. Or, theorem. Okay. Let R be a finite integral domain. Then R is a field. Okay, I think I did mention, but I want to emphasize it once more, that from now on, all rings are non-zero unless we specify it, right? From now on, 1 is different than 0 in the ring R, right? You remember that? I said this, that from now on, all the rings, the identity for the multiplication will be different from the identity and for the addition. Okay, from now on, unless I explicitly say this is the 0 ring. Okay, then R is a field. Now, how do I prove that? That's an important proof. Let A be an R, A different than 0. What do I need to show that something is a field, that a commutative ring is a field? What do I need to show? Yeah?
That I can find a B in R such that AB gives 1 R.
Equal to 1. So I need to find the multiplicative inverse for A. If I manage to find that, then I already proved that A is a unit. Well, I didn't say the word unit yet. That A is invertible, okay? So, and I know that the finite integral domain is obviously a commutative ring, right? When I say integral domain, it's an underlying assumption that my ring is commutative already. Okay, in the definition, we define integral domain for commutative rings. Okay, so let A be an R, A different than 0 R. Now, let F be the function from R to R. Be the function that sends x in R to AX. Okay? Just multiplication by A. You take an x and you multiply by A. Is it clear? Here x in R, so it sends x in R to R. A times x, it makes sense, right? Because I'm in a ring, I can take the product of two elements. Are we good? What can I say about F? I will show that F is injective. F is injective. Why is that? If x and y are in R, if x, y, and R, and fx is equal to f of y, what do I get? I get that ax is is equal to ay. Isn't that right? Fx is equal to fy means that ax is equal to ay. In the ring, I can subtract elements, right? I can subtract elements. I can. Agree or not? So far, so good. Now I can factor an a out. Isn't that right? Did I do anything wrong so far? So far, so good. Great. Now, R is an integral domain. So what can I say here? Yeah?
That A has a multiplicative inverse?
Not necessarily. If R is an integral domain, can you say that A is has an inverse? That's what you want to show. Integral domain, is that clear? Integral domain. Yeah?
It has no zero divisor.
It has no zero divisors. Very good. So what can I say here? Yeah?
Does not exist.
Yeah?
A 0 or x minus y.
Exactly. So A is 0. Or x minus y is 0. Agreed? Everybody?
Yes.
Now is A equal to 0?
No.
No. So what is 0? X minus y. So x minus y is equal to 0r, since A is different than 0 and R is an integral domain. Very good, thank you. Is an integral domain. Now x minus y is equal to 0, what does it imply? It implies that x is equal to y. Hence, x is equal to y, and f is injective. Okay? Now R as a set is a finite set, right? F from R to R is injective. And R is finite by assumption. Agree or not? What can I say about F?
It's surjective. It has to be surjective.
That's right. We see this or not? If you have a finite set, I mean you can prove that, but a proof by picture works well. If you have a finite set, say with 3 elements, and you have an injective function, then it must be surjective. Yeah? I think we saw that in analysis. Yes, sir?
Because R has the same cardinality as R,
Exactly.
and hence the injectivity means
Exactly. And R is finite. The most important part is that it's finite. If you replace it by infinite, if R is infinite, that's not true anymore. Okay? You can find an injective function that is not surjective from Z to Z. But the most important part, that R is finite, and you have an injective function. Is that clear, everybody? Yeah? And R is finite, hence F is surjective. Therefore, there exists x0 in R such that f of x0 is equal to 1R. Agree or not? This is surjectivity. 1 is an element of R. Since f is surjective, I can hit it by some x0. Agree or not? Is that clear? Yes or no? Yeah? Any questions on that? What is f of x0? What is f of x0 by definition?
It's A.
Ax0. Very good. Oh, wait a minute. I just found an inverse for my A. Ax0 is equal to 1. So I showed that A has a multiplicative inverse. Okay? That's an important proof. Okay? I mean, we'll see an argument like that afterwards. So Ax0 is equal to 1R. Hence, A has an inverse. Of course, we're working, an integral domain is commutative. So x0a and Ax0 are the same. As an inverse. Hence, A has an inverse. As a multiplicative element. Or as a multiplicative inverse in R. So R is a field. Very good. Okay, please know this proof, it's a good one. When you know next term you might see things like that. You might use when you study like integral, when you study fields and integral domains, those proofs become handy. Yes?
Are you teaching 236?
No. Okay, but those might, those usually show up in linear algebra. Okay, when you study rings as vector spaces, anyways. Sorry, yeah, anyways, let's not worry about this now. Okay, is that proof clear? Is it clear? So please do know it. It's an important one. Great. Okay. Okay, so now so corollary. Let B be a prime number. And Z mod PZ is a field. We proved before that Z mod PZ is an integral domain, right? You remember this? Z mod PZ is an integral domain. Z mod PZ is a finite integral domain, so Z mod PZ is a what? A finite integral domain is a field. So Z mod PZ is a field. Okay, good so far? So far so good? Great. Now I'll introduce the group of units. Okay, it's going to be a bit quick. Units in a ring R. Okay, so let R be a ring, not necessarily commutative. An element A in R is said to be a unit in R if there exists a B in R such that AB is equal to BA is equal to 1. Basically, A has an inverse in R. Okay. Now, for commutative ring, it suffices to satisfy one of them. AB is 1R, so BA will be 1R, right? If R is commutative. Now, in non-commutative rings, we will give examples maybe in the next lecture. We can talk about right-sided and left-sided inverses, but let's not worry about that too much. We'll just worry about this. Okay? We'll mostly work with commutative rings, so it's a safe assumption. I don't want to say it's a safe assumption, but it's, yeah. To assume that the ring R is commutative. Okay? Just to make things a bit easier. Okay, now the set of units in R is denoted by R star or R cross. This is the set of units. Proposition R star under multiplication is a group under multiplication. Okay? You can multiply two elements in R. Now if you take all the units, you get a group under multiplication. Okay, so let's do that. So first, let xy be in R star. I just need to show that x and y, that xy is in xy, that the product xy is in R star. Okay, so x is in R star means there exists prime in R such that x prime is equal to x prime x is equal to 1R. Y in R star implies there exists y prime in R such that y prime is equal to y prime y is equal to 1R. Now you know what's the candidate for the inverse of xy?
Y prime x prime.
Y prime x prime. Very good. xy times y prime x prime. What is that equal to? This is just x y prime x prime, which is x 1r x prime, which is just x prime is equal to 1r. Okay? And then y prime x prime times xy is equal to what? Is equal to y prime x prime x times y, which is just y prime 1r y, which is just y prime y times 1. Okay? Now also 1r belongs to 1r belongs to r star, since 1r times 1r is equal to 1. Yeah? Are we good so far? Now how I define the inverse of x? X prime, right? If x belongs to R, this implies that x prime also belongs to R, right? So it's closed under taking inverses as well. Are we good here? Yeah? Is it clear? Yeah. Yes?
So this too basically eliminates every single set for which there does not exist such a prime, right?
Such a?
Every element A for which it does not exist.
Exactly. So the group of units is just the ones that are invertible.
So it's a subgroup?
It's not a subgroup.
It's not?
It's a group on its own, because when you say a subgroup of R, it should be under addition, right? R is a group under addition, not under multiplication. It's a subset of R, and it's a group under multiplication. Of course, you can show that the x primes are unique, right? Just like you did, x prime is unique. Just like we did for groups, okay? Great. So far, so good? Yeah? I mean, you don't really need this actually. You have an inverse, and it's associative. And associativity follows from properties of times. I mean, well, you can say that, yeah, I mean, x prime also belongs, no, you need the time. X prime belongs to R, since x prime is x prime and x is 1. No, you need that. Okay? So this is a group under multiplication. Okay. Now let R, or Larry, let R be a commutative ring. Commutative ring means what is commutative? The multiplication, right? Everyone, are we good? Commutative means multiplication is commutative. Now if R is a commutative ring, then R star, with respect to times, is an abelian group. Okay? Because the operation is commutative, so multiplication will be commutative in R star. Okay, great. Should we do a proof like the integral domain proof? Do you want to do a small proof like that? We could do that. So injective, surjective, nice things.
Mm.
Should we do one like that? Let's do one like that. It's a very nice, very cool argument. So, proposition. We know what zero divisor is, and we know what unit is. Okay? Zero divisor means it's a non-zero element for which you can find another non-zero element, such that the product of the two is zero. Right? Unit is an element that is invertible. I could find an inverse for it under multiplication. Okay? Now, let's prove this proposition. Let R be a finite commutative ring. Because I only define zero divisors for commutative rings, right? So let R be a finite commutative ring. Then any non-zero element is either a unit or a zero divisor. Okay? So if you have a finite ring, finite commutative ring, then any element, you can class any non-zero element. You can say it's either a unit, it's either invertible, or it's a zero divisor. Now this fails in infinite rings. Can you give me an infinite ring? What's the simplest infinite rings that we know? R or? Z. Let's pick Z. Because Z is not a field, so I'll try to work with Z. Now does Z have any zero divisors? If AB is equal to 0 in Z, can you say that A or B is equal to 0? Yes. So does Z have any zero divisors? No. Very good. Now, is every non-zero element of Z a unit? Is 2 invertible in Z? Could you find an inverse for 2 in Z?
No.
2 times something. Can it give you 1 and this something be in Z?
No.
No. So 2 is not a unit. Are we good here? Yeah. So this fails in infinite rings. Okay, let's prove this. Proof. Let let A be non-zero. Let A be non-zero belong to R. Well, let A belong to R. And A is different than 0. Then let A belong to R and A is non-zero. If A is not a unit, if A is not a zero divisor, we'll show that A is a unit. Okay. Now how do we proceed? Look at the previous proof. Let's define a function that sends x to ax. Let's do this. It's the same argument. Let f from R to R that sends x to ax. What do I need to show here? That f is, I'll need to show that f is surjective, but how do I show that? By showing it is injective. F is injective. Why is that? If fx is equal to fy for some xy in R, what can I say? I say that ax is equal to ay. So it's ax minus y is equal to 0 R. What do I need to conclude? I need to conclude that x minus y is equal to 0. Do I have that? Can I do this conclusion?
Yes.
Why?
Because A is not a zero.
A is not a, very good. A is not a zero divisor. So x minus y must equal 0R, so x is equal to y. Great, it's the same song again. R is finite and f is injective. R is finite. And f from R to R is injective. Hence f surjective. Hence there exists x0 in R such that what? A f of x0 is 1R, so A x0 is 1R. Okay, so A is a unit. Okay, so far so good? Great. Okay. So please, these are important. This idea of x times ax showing it's injective and then it's surjective and then, it's an important idea. Okay, it's very important. Please be sure to know that. Okay. Great. So we're done with the basics. I mean, you can give a small example here. Consider z mod for z. What are the units in z mod for z? What are the invertible elements? We saw this. We saw this before. The units of z mod for z. 1 and 3, right? These are the invertible elements. Those are the ones who have GCD an is equal to 1, right? We found an inverse by using the Euclidean algorithm. Do you remember this or no? You remember that? No? If GCD an is 1, you can write AU plus BN is equal to 1, right? Reduce mod n, you get that AU is congruent to 1 mod n. So U would be the inverse of A mod n. You remember this? Yeah? Yes. Let's redo that.
No.
Let's redo that.
No.
Let n bigger or equal to 2. Then z mod nz star is just un. Okay, un is the group of the un. What is un? This is just the set where un is the set of equivalence classes of A mod n, where in GCD an is 1. We showed that the GCD does not depend on the representative, right? You remember that? Yes? Okay, so please try to have a look at this again. So let n be bigger or equal to 2, then the group of units, this is why we call it U, by the way. Why do we call it U? Because of units. Right? This is why we call it U. The units model. Okay, so let's prove that. So suppose let A being Z such that GCD an is 1. So basically A belongs to un. Agree or not? Now then, there exists UV and Z such that AU plus NV is equal to 1. 1 is the GCD of AN, right? Remember this, the Euclidean algorithm? Yeah? Reduce mod n, hence AU is congruent to 1 mod n. which means that the class of A times the class of U is equal to the class of 1 mod n. So A will belong to Z mod n Z. Okay, you remember this or no? Yeah, we did this. Okay, now let either in assignment or in class, but I think you did this, right? Either in a homework or in class. In class? Okay. So now, so we proved here that Un is contained in Z mod n. Un is contained in Z mod n system. Now suppose A belongs to then there exists what do you want to call it? Bn, say. Bn such that the class of ABN is equal to 1 mod n. Right? So, is it clear? Should I leave it as an exercise? Okay, I'll leave the remainder as yes.
Just a question, does it matter the way you write subgroup? Because sometimes you write it like,
Subgroup?
it's a subgroup and you
Where?
contain.
Yep, contain. Yep, this is a set. So AB is equal to 1. Why is the GCD of A and N? Yeah, so there exists
We expanded
A in Z such that AB is equal to 1 plus Kn, right? So AB minus Kn is equal to 1 by Bezout. GCD Kn is 1. Yes, sir.
I mean, we would say it divides 1, and then conclude it has to be 1.
Yeah, that's okay. If you had a other number than 1, then yeah. I mean, we can put it this way if you want. If you don't want to name theorems, of course, sure, we can do that. Hence, GCD AN divides 1, so GCD AN is 1. Okay? So, A belongs to UN. Okay? Hence UN is Z mod and Z star. Okay, great. So please, we should not forget that we have 2 months of groups before us. Okay? I'm going to heavily rely on those. So I'm going to do the ring part with groups. Okay, so it's very important that you know your group theory. Okay? So let's continue with the example. What are the units of Z mod for Z? Example, Z mod for Z. What are the units? 1, 3. What are 0 divisors?
2.
2. And we have the 0 element. Okay? So every element is either 0, a unit, or a 0 divisor. Okay, is that clear? Very good. Yes, sir.
What about the converse direction? Like we proved that it's not a unit and it's
We proved that if the GCD is oops, no, I had it here. I proved that I proved that Z mod n Z star is contained in UN. Right? This one here. And this one here, I proved that UN is contained in Z mod n Z star.
So for like every element being either a unit or a zero divisor.
Oh, so if it's not a zero divisor, then it must be a unit. So the proof starts, let A be non-zero. If it's not a zero divisor, then it must be a unit. Okay, is that clear? Yeah. Yes?
Wait, but for that, don't you also have to prove something else? Like, if it's not a unit, and it's not a zero divisor, but you also have to prove that it can't be both.
Well, I mean, oh, okay. I mean, it's clear that it can be both because, I mean, yeah, but that's a good point. So a unit is never a zero divisor. That's a good point. Thank you. Right. Suppose that AB is equal to 0 and A is a unit. Then you can multiply on the left by, right? So if a unit is never a zero divisor, so suppose A is a unit. Suppose A is a unit, and let B be such that AB is 0. Okay? Let U be such that AU is equal to 1. Multiply by U on both sides. So UAB is equal to U times 0R, which is 0. UA is 1, so B must be 0. Okay, so if it's a unit, it's not a zero divisor. Okay, thank you very much. That's an important remark. Maybe it's not so obvious. Okay. Yes?
Just really for Z mod 4 Z in this case. So you mentioned the units are the class of 1 and 3, right?
Yes.
Is it also like the generators?
The generators of a cyclic group Z mod 4Z. That's right. Yeah. That's right. In that case, yeah. Okay. Now let's look at ring homomorphisms. Or before I start, did you guys see complex numbers?
Yeah.
Have you ever seen complex numbers? Okay, so we'll just do a small recap on complex numbers, very quickly. Who has never seen complex numbers? Okay. Don't hesitate to raise your hand. Raise your hands if you haven't seen. Okay. So we'll just do a small recap on complex numbers. Have we all seen the imaginary quantity I? I squared is minus 1. Okay, so let's, we can give a small, I mean, we should do some complex numbers here.
I mean, sir,
Yes?
did we already even see quaternions on that homework?
Yes, but quaternions come from a group, basically. It's just a symbol. So complex numbers will just work as a symbol. Okay? So, see complex numbers. Okay? So first of all, let I, let's say, be a symbol for now, such that I squared is minus 1. So I is a symbol. When you square I, what do you get? Negative 1. Okay? A complex number is an element of the form x plus iy, where Okay? We have seen this definition before. Anybody took linear algebra, so like basically C is a two-dimensional vector space over R. Did you ever see that definition also? Yeah? No? That's okay. You can see that, that's okay. So a complex number is an element of the form x plus iy, where x, y, and r. Now, there are properties of complex numbers. How I add two complex numbers. So plus x prime plus iy prime. How do I add the complex numbers? How do I add these two? Add them up. Just naturally. How would you add them up?
Pairwise.
You add them pairwise. Just x plus x prime plus y plus y prime. This is how you define addition of two complex numbers. Basically, it's just a pair of coordinates where you have a multiplication that's a bit weird. This multiplication is a bit weird. Okay? Now how do you define the product of the two complex numbers? Times how would you take the product of these two? Just expand it regularly. Okay, just expand the two things regularly. And replace, whenever you have I squared, you replace it by minus 1. So how do you, what is the multiplication of these two? So let's say this is x prime minus y prime plus I x prime y
That's not how you explain.
plus I y x prime. Oh, sorry, y prime x. Yeah. Okay? Have we seen this before? Have we seen this? No?
I can't
Okay.
see that way.
We never saw it. Okay. Now, what's the identity for multiplication? If you let 0 here and 1, if you let 0 for y prime and 1 for x prime. Yeah, I thought they did this in linear algebra. They do complex numbers in what's linear algebra? Math 133? They don't do that. Okay. CEGEP, they don't do that?
No.
No? You do complex numbers in CEGEP?
Not really.
Well, okay.
It varies.
Okay, I mean,
We didn't do a whole lot.
great. I mean, let's take an example. Let's take a small example, and let's try to multiply two things. So let's pick a number. Anybody can give me a number?
2, 3, 7.
Someone? Yeah, go ahead. Yeah, number? 2? 2, 3. You said 7?
Yes.
2 plus 3i. 7. Someone can volunteer. Another number? 5. Okay. 7 plus 5i. Let's multiply those two things. Just multiply them as you would multiply the sum of two numbers, an expansion of two things. So it's 2 times 7, what is that? 14. 2 times 5i, what is that? I is a symbol. 2 times 5i, what do you get? 10i. Okay, 3i times 7, what do you get? 21i. Okay, 5i times 3i, what do you get? It's 15i squared, right? Agree? So far so good. We all know how to multiply these two things, like regularly. Okay, now the I squared, what do I replace it by? Minus 1. So 4, 14. Add the i's up, what do you get? How many i's? 31. 15i squared is minus 15. So this is just minus 1 plus 31. Okay? Is it clear? Is it clear how to multiply those two expressions? We do one more? Should we do one more? It's clear, right? It's easy. Multiply those two expressions. as you would multiply two regular expressions, and just replace I squared by minus 1. That's it. How do you add these two? What's 2 plus 3i and 7 plus 5i? Add them up, what do you get? 9 plus 8i. Is that good? Is it clear? Yeah? Okay. Now, I'll leave stuff as an exercise for you. Let's see. Let's do an addition here. Plus 7 plus 5i, what is that? This is just 9 plus 8i. Now, what's the neutral element for addition? 0 plus 0i. Right? What's the neutral element for multiplication? 1 plus how many i's? 0 i's, right? Yeah, x plus. Just multiply them naturally. How we would multiply them? How did you learn to multiply? What do you call this? Foil expansion or something? How would you foil expand this? By just replacing the I, squared by minus 1. Whenever you have an I squared, you replace it by minus 1. That's the rule of multiplication. What is that? This is x. Right? Look. X plus iy. Okay? Is it clear? Is it clear how to multiply these two things? Yes? Or no? Is it clear? Okay, now. Okay, so I'll continue on complex. Maybe I'll give you the properties of complex numbers next time. Okay, I'll continue with complex numbers next time. Define the modulus, show when x plus iy is 0, and things like that. Okay, so now I need to talk about the final. I have like 3 more minutes, so that's what I planned. Okay, if you want to listen, you can listen because I will not record this.